Okay, now that we learn what kind of combination of acids and bases will actually create a buffer, the next step we need to learn is how to calculate the pH of a buffer solution. So if I tell you that I make a buffer with a weak acid and its conjugate base, what's the pH of that buffer solution? We're going to work out the concept of calculating the pH of buffer using this problem right here. And the problem is split into three parts. The first part is to calculate the pH of 0.1 molar acetic acid, and then to calculate the pH of 0.1 molar sodium acetate, and then lastly to calculate the pH of a buffer that has both the acetic acid and the sodium acid. Okay, so part A and part B, those calculations are already done in the prior chapter. In fact, if I ask you about part A, all that is just a weak acid pH calculation, which hopefully you're pretty comfortable doing at this point. Our weak acid will dissociate into these two species. We use our 0.1 concentration minus x, we set it equal to Ka. So at the end, we should get this as the value of x once we make our small k assumption. And that happens to be our H plus. So pH is just a negative log of that number, and it's going to be 2.87. And this number should make sense to you. It makes sense because all we're dealing with in this solution in part A is just a weak acid. Okay, so weak acid should have a pH less than 7. Now, if you look at part B, we have sodium acetate. What is sodium acetate? It's a salt that breaks apart into sodium and the acetate ion. You remember our discussion about salt previously, that this is neutral and that the conjugate base of a weak acid, which means that it's going to be a weak base. So we can calculate the pH by writing the weak base reaction with acetate as our base. So that's just acetate in water forming the conjugate acid and OH minus. And again, the K of this we can calculate because the K of this is called the Kb of acetate, but that is something we can calculate by using the Kw over Ka of the acetic acid, which is conjugate acid. And so, in fact, that's what we did here. We found Kb using Kw over Ka, and we end up getting 5.56 times 10 to the minus 10 as the Kb value. That whole thing has to be set equal to the equilibrium expression, which is this concentrations right here, set up as x squared over 0.1 minus x. Using the small k assumption, we end up getting 7.45 times 10 to the minus 6 as the hydroxide concentration. And so pH is going to be 14 minus POH, which is 8.87. And again, this number should also make sense to you because in part B, the only solution we have is sodium acetate, which is just a solution of a basic salt. We expect a basic pH when we calculate. Now here's the new part, just the perhaps more difficult part, and that is the buffer. We mix these two things together and we're trying to figure out what is our buffer. In part A, the equation we use to calculate, set up our ice table is the weak acid dissociation. In part B, the reaction we use is the weak base reaction with water. What about in part C? Which reaction should we use? Well, it turns out that doesn't matter. We can use the weak acid reaction or we can use the weak base reaction. Both will give us the same answer. So let me just show you how. Using the weak acid reaction, I'm going to figure out what I have originally. So remember, this is the weak acid reaction. Weak acid producing H plus and acetate. The only difference between this and part A is that now, not only do you have 0.1 molar of the acetic acid present originally, but you also have 0.1 molar of the acetate originally present. Where's that acetate come from? It comes from the 0.1 molar of sodium acetate, which dissociate completely to form sodium and acetate. And so therefore, at the beginning, you already have some acetate present. If you do your ice table with minus x and plus x, you're going to get 0.1 minus x and 0.1 plus x at equilibrium. And all you need to do is set that equal to your Ka expression. So it's going to be x 0.1 plus x over 0.1 minus x. If you use a small k assumption here, this is just about 0.1. This is just about 0.1. Matter of fact, those two cancels out. So your x is just equal to the Ka of acetic acid, and the K of acetic acid is 1.8 times 10 to the minus 5. So your pH is just going to be 4.74 because that number is your H plus concentration. Now, what you have to think about is the pH of the buffer is 4.74. The pH of the weak acid alone is 2.87. That should make sense to you. Why? Because in the buffer, we have the weak acid and its conjugate base. So we're adding some base to the acid original. So if the pH of the weak acid is 2.87, the pH of the buffer should be higher than 2.87 because we've added some conjugate base to that solution. So in fact, having 4.74 as our pH makes sense. Now I'm going to show you how to do the buffer calculation with the weak-base reaction. You start with that same weak-base reaction you used in part B earlier, acetate plus water forming acetic acid and hydroxide. The difference, you have both acetate and acetic acid, just the same way as when you start this other ice table here with method 1. You have both of those acid and conjugate base already present. Working out your ice table, you end up getting quantities at equilibrium. Now you're going to have to set them equal to Kb because this is a base reaction. So it has to be set equal to Kb. So it will be x times 0.1 plus x over 0.1 minus x equals Kb. Using the small k assumption, these two things basically will cancel away because it's just become 0.1 over 0.1. So your x here is going to be Kb, but your x represents hydroxide concentration. So if hydroxide concentration is 5.56 times 10 to minus 10, then you can use pH equals 14 minus POH to get the pH value. And surprise, we get exactly the same number, 4.74. Look. Previously, we got 4.74 for the value of the pH of the buffer. Now we get 4.74 again. So we have to get the same number. We can't get different numbers when we're using different methods because we're calculating the same solution, right? So either method 1 or method 2 gives you the same answer. Method 2 takes a little bit more time because you're actually calculating OH minus, and then you have to convert that OH minus to pH. And you're also using Kb instead of Ka. Given these two choices here, it'd be easier to use method 1. Now we're going to derive a formula to calculate the pH of the buffer, and that's called the Henderson-Hasselbalch equation. It's not that this formula is a new method. It's really just derived from that ice table approach that's used. But sometimes when it's given in the form of formula, people like using it because it's easy. You can just plug in some numbers straight into given formulas. So we're going to start by writing our weak acid dissociation reaction, which hopefully are really familiar with at this point. Is HA goes to H plus and A minus. And remember that what do we have in a buffer? We're supposed to have a mixture of HA and A minus floating around. We have some counter ions there for the A minus, but that counter ion is not going to play a role. So we're just writing HA and A minus there. Or of course, we can also have NBH plus, a base and a conjugate acid. Either way, this equation is going to work. So we're going to start with HA and A minus. The reaction is going to look like that. We're going to have some quantity of HA at the beginning and some quantity of A minus at the beginning. We have to. In order for it to be a buffer, both of those things have to exist. According to our ice table, this reaction has a K equals to Ka, which means that it's much less than 1. So therefore, change is going to be minus plus X in this case. And so at equilibrium, I'm going to have initial concentration minus X for the acid, initial concentration plus X for the conjugate base, and then just X for the H plus. And then usually when we have this equation, we would set it equal to Ka. And so Ka will be equal to X times A minus initial plus X over HA initial minus X. And remember what we did in the prior problem. When we see this, we say that we can use our small k assumption. So this is roughly just going to be equal to that. And this is going to be equal to just the conjugate base initially. So the equation simplifies into Ka equals to X, but X is just H plus at equilibrium, times A minus initially over HA initially. Okay, that's this equation right here. Now, what I'm looking for is pH, so I want to isolate H plus on one side. If I do that, this is what I have. I have H plus concentration equals to Ka times HA naught over A minus naught. Okay, then that's the point when I want to take negative log of both sides. Log of all of this right here. When I do that, I can separate out the negative log of just Ka with the negative log of all of these guys right here. The ratio is what we call it. And so that's shown right here. This is the negative log of the H plus on the left side, negative log of Ka, and then negative log of the ratio. Negative log of H plus is just pH. Negative log of Ka we will call pKa. Remember this quantity we discussed in the prior chapter on acid-base equilibrium. And then the negative log of HA over A minus we will flip. We would take the negative into the log and make it the reciprocal. So now it just becomes a positive log of A minus at the beginning over HA at the beginning. This equation is usually written without that naught symbol. So it's just written like this. pH equals pKa plus the log of A minus over HA. That is what we call the Henderson-Hasselbalch equation. And this is a really useful equation to calculate the pH of a buffer, but keep in mind, only works for a buffer. So don't apply this equation on some weak acid problem or weak base problem. It has to be a buffer before you can use this equation. So let's see how we use the Henderson-Hasselbalch equation to calculate the pH of a buffer. So remember that in a prior lecture, we had seen the pH of a buffer that was made by 0.1 molar acetic acid and 0.1 molar sodium acetate. That pH happens to be 4.74. So I'll just scroll back up here to show you how we got that pH. So it was calculated here, and then it was calculated again here using an alternative approach. But both of those gave us a pH of 4.74. Now we're going to use the Henderson-Hasselbalch equation to see if we can just get the same number. The Henderson-Hasselbalch equation is pH equals pKa plus the log of A minus over HA. The pKa is going to be the negative log of the Ka. The Ka has to be the Ka of the acid in this case. So acetic acid is the acid that we are using. The Ka, if you look it up in the K table, is 1.-5. The concentration of the A minus over HA is just the concentration of the conjugate base over the concentration of the weak acid. Our conjugate base is acetate, or weak acid is acetic acid. They both happen to have values of 0.1, so that's going to cancel away. So it's just a negative log of 1.8 times 10 to the minus 5. That's our pH, and it's indeed 4.74. It's the same answer, whether we use that ice table approaches with either the weak acid or the weak base reaction, or if we use the Henderson-Hasselbalch equation, we get the same exact answer. But people like this because you can see that it's a much shorter route to get to your answer, just plugging in some numbers into a formula.